Hi, Mike Denninger here, back from the lighting design workshop, and here we're designing solid state light bulbs, so LED based light bulbs, and this is a 9-part series. That series, when you're done, you'll be able to handle electrical design and thermal, optical, mechanical LED device, and be able to design your own light bulb for a lot of the cool smart home products that are going on out there. So in this lesson, we're going to learn about how to calculate the operating temperature of a light bulb. And one might ask, why will we do that? Or what importance does it have? And there's a few things. One is, the first one is safety for ourselves of just handling it. So temperature when you can touch something. And secondarily, it's the reliability of the product. So parts inside of it will last longer or less depending on how hot they get. And there's also the UL component of it. So if you're gonna list a product for safety regulatory work, then that has to have meet certain temperature requirements. But the first one is the one that's most important. And that one, this graph will probably describe that pretty nicely. So that is a graph of temperature and time. And I've noted in larger text here, 70C is basically 0 seconds. So you will, if you touch them at 70C, you'll get burned immediately. It's a burn on impact kind of thing. And then 60C, at about 3 seconds, about right here, you will have 3 seconds before you'll get burned. So this graph is quite important from a product design standpoint, from almost anything, not just solid state lighting products, but anything that has a component of temperature, and you might handle that. So in this case, we're talking about a light bulb, and you might screw that light bulb in and touch it, or more importantly, when it's been running for a long time, touch it. So that's an important component. So we're gonna do basically, for this short lesson, we're gonna do a first order approximation using Newton's law of cooling, and that will be based on the amount of power that's going into the light bulb and its ambient condition. So in this case, the ambient condition is the light bulb is sitting vertical in a lamp, and it is in free air conditions, so air just flows around it, and that we can handle with some more straightforward calculation. So what Newton's law of cooling looks like is this guy right here. So Newton's law of cooling is heat input, so that's heat that's not used to generate light, or energy not used to generate light, that's now waste heat, times heat transfer coefficient, times the surface area of the bulb, times the temperature difference. We're going to calculate the temperature difference based on these three guys. So, and the surface area of the bulb is going to be this guy right here. So, are there any questions with regards to Newton's law of cooling in terms of how we're doing it here? Okay, so the question that's asked is, does Newton's law of cooling apply for this condition and this one and this one? And the answer is all three, but the heat transfer coefficient does vary based on those, and the temperature will vary. So, and that's something we'll do, since this is a first order, kind of a first pass on it, we'll do that in the next lesson, where we'll look at more details about specific conditions and how they may affect our first order calculation. So using Newton's law of cooling, we can calculate temperature difference. So that'll tell us how much it rises, and we need to consider the ambient condition for that. So you can think of it as a parallel. Maybe if you put a pot of water on a stove and you turn it on, if you're in Alaska, you'll have to turn it on to a higher power than if you're in Texas to get the same temperature in that water. So in this case, we need to know that ambient temperature. In this case, we'll use 20C as a baseline temperature for that. And using Newton's law of cooling, which we just saw, we'll calculate it in this fashion. So again, Q equals 7.5 watts. So that's energy that's left behind after we generate light. So whatever doesn't get used for that. Heat transfer coefficient, this comes from a table for that condition when the bulb is standing straight up. And area we calculate right up the bulb. So in this case, it's a small number, but it's 0.032 meters squared. And that's only because we're using the metric system, MKS, meters, Kelvin second, and so on. So it looks small, but it's actually a decent sized area. And so using that and those inputs, temperature difference is calculated to be 40 C. And 20 C ambient means it's 40 plus 20 or 60 C. So that works quite nicely if we go back to our original graph. This guy right here. 60 C gives us 3 seconds if we touch it. This is a pretty safe bulb to handle. So if something happens and we try to unscrew it and it's been running, we'll be okay. So that is a first order approximation of that. Are there any questions the way we did that? Okay, so as a recap, what we learned was calculating the temperature of a light bulb in open air is very achievable using Newton's law of cooling. It's pretty straightforward, and we need to take stock on a few things that are from literature. So heat transfer coefficient, open air, and so on, and the orientation of the bulb, and burn limits for handling things are quite important and should be part of any design. So, and we looked at a graph and we know what that means now. So anytime we calculate something and we see it to be 80 or 90 C or something, we know we should be concerned that that probably shouldn't be directly accessible to people. So in the next lesson, we're going to dig a little deeper and learn how to deal with different conditions. So if the bulb is not in the right orientation or the same orientation we did, if it's in this orientation here, this one, or if it's sealed, if it's in a sealing fixture and it's got glass on it, or it's outside and it's sitting in your, like a pendant bulb, something outside in a driveway or something. Those lights are sealed and the sun on them and so on. So we'll look at details like that, and we'll also look at how to test that. So we'll look at test conditions. So thank you for your participation, and we'll see you next week.